presentation, like if you raise your hand, or like ask a question, or maybe even answer a question, if you're so moved, you can like ask for a Twix. They're not packaged like individually, so I could throw them, but it'd probably be better if you came up and like actually like received them individually. Is that fair? That makes sense? Okay, cool. So I'm going to start up with a question. Now I'm being recorded, so what realm, like,
this is the whole whiteboard, so you got a lot of space.
The whole whiteboard.
Yeah.
All right. A long lead. All right. So the question that I'm going to start out with is, which is more important, right? Knowing where you're going. So the question is, which one of these is more important? Knowing where you're going. Or getting there fast. Okay, which is more important? Knowing where you're going or getting there fast? Let's have a couple, like, what do you guys think? Thoughts?
Let's have some opinions.
Yeah.
Knowing where you're going.
Knowing where you're going, why?
Because you don't want to accidentally run into someone unexpected. You don't want to run into someone unexpectedly and accidentally hurt them.
Okay.
Because getting there, because that's even worse. Because then that could cause an accident. That's even worse than maybe say getting to a place late. So just getting there fast is always important. So knowing where you're going is more important.
Okay, so there's a risk. If you only optimize for getting there fast, you can be reckless and cause accidents, right? Any other opinions? Yeah. You want to?
I guess it's also important to work on, getting there fast, because really cautious, because getting there fast doesn't necessarily mean that you might harm someone. Like, you could work on it, I guess. So yeah, getting there fast is also an important aspect.
Okay, so as much as it's important to know where you're going, getting there fast is something that you shouldn't completely neglect, right? Okay, in the back.
If you know where you're going, you know whether or not like if it's a trap or not. Like if you're going there fast and you don't know where you're going, you just be setting yourself up for something bad.
Okay, so this keeps you away from places that you don't want to wind up in, right? Okay, good. Maybe a couple more comments and then we'll move on. Go ahead.
If you simply focus on getting there fast, you might end up taking a long route than like knowing where exactly you're going first, because you don't know where you're going. So I think getting there fast is important, but knowing where you're going is more.
Very good. So like actually knowing where you're going actually helps with getting there fast, right? Because if you just optimize for speed, you might go fast on a very, very arduous and circuitous like highway, whereas a back road might get you there faster, right? So knowing even like the way of getting there. All right. One more. I think there was one more hand in the wall.
I think both are important throughout any journey because you need to find the perfect balance between those, and they're specific to each person and the way each person is.
Okay, so both are important, okay? So one of the things that I try to organize my life around is, first of all, knowing. I think that of the two, this is probably the one that like requires probably a bit more emphasis, right? Because getting there fast, this is like sexy, right? This is like, oh, I'm faster than you. We had a race, like maybe the Olympics, and Lance Armstrong finished first, and. But at the same time, like knowing where you're going, this is the part. This is the introspective part that maybe people don't like glorify so much. It's the part, like when you sit down and you journal, maybe. When you sit down in the morning, you think about like, oh, what are some of the things I need to do today? When you sit down, like after you write the email, you sit down and you read it again to make sure that you didn't say something that would actually harm you, right? So I think that this is like a part of our lives that a lot of times we neglect. Now this can show up. Knowing where you're going can show up in quite a different number of ways in our lives, right? So what are some ways we can think like metaphorically or like very like concretely about like knowing where you're going? What are some things that people do to like better know where they're headed? And I'll leave that question intentionally vague so that we can take a look from different angles. What are some things that people do to know where they're headed?
They copy. They copy somebody else's journey.
Oh, I see. So they research what somebody else has done before, and they learn from that and apply it to their lives so they don't have to make the same mistake. Okay, good. Otherwise, what are some things that people do to know which way that they're headed?
Plan out a schedule.
They plan out a schedule, right? So sometimes they take like a piece of paper or a calendar and they'll write down to make sure that they're not double booking themselves.
What they've done versus what they want to do.
Okay, so they'll take time to like review and say like these were some of my objectives, and then they'll have like a quarterly review or like a weekly review where they'll sit down and think about where they're going.
They
can have a GPS?
They can have a GPS, a global positioning system. Very good. That's a very concrete way that people know where to go. Good, good. So sometimes they'll like sit down with like a coach and then they'll take a look at some of the things they've done before, and the coach will help them identify places that they can grow, something along those lines. Yeah. A map, right? Like the more or less like, you know, like copying somebody else. Somebody else has already gone through and scoped it all out, and you're merely referring to some other things. I think that's really cool that a lot of times people will work together on a project, people that have more seasoned experience and some people that are more novice, that the people that have been there before can share some of the mistakes with others. If you guys don't already have a mentor in your life that can do some of the things that we just discussed, I think it's really important that you find mentors. One of the things that I do, I find really important, is to meet with my advisor at Stanford frequently, but that's more just like professional, right? And if you're only looking at just, you know, like my academic success, you might be leaving out some other parts in your life. So I know that I have a group of friends, and every Friday evening, there's like 20 of us, and we all get together and we share like some of the highs and lows from our week, and we encourage each other. And a couple weeks ago, we were like all like forcing one person to quit his job because it was like, you know, ruining him, and then like sometimes there was something like relationships, and we'd like all counsel each other through that. So these are really important. But that's not why I've come to talk to you today, because BlueStamp Engineering is about engineering. So we're gonna talk about engineering, but they gave me some food, and if you guys have time or interest afterwards, you want to talk to me about anything other, any of these, you know, knowing where you're going, I'm more than happy about that. So knowing where you're going. So we mentioned two things. We mentioned a GPS. We mentioned a map. What are some other technologies that people use if you want to build a system like an aircraft or a car or a boat? What are some other technologies that people use to know where to point the thing? We'll just make a list. Okay, so we talked about a GPS, a global positioning system that uses satellites, right? And we talked about a map. All right, other ideas?
We could use
Infrared, so like LiDAR sometimes works this way, right? You have like, you know, one of these Google cars, Waymo, and they're driving around, there's like a little laser that's spinning around, and it's seeing, you know, reflections off of different ideas to map out what's nearby. Good. So LiDAR, and this is good for avoiding obstacles, right? Infrared. Good. Other technologies that people use to know where they're headed.
a windshield.
A windshield, right? Just looking at like your eye. Windshield. You know, on a submarine, this might be a periscope, right? Those little like tubes that come out, they, you know, look above the water. Windshield. In the back. Yeah.
Drones.
Drones. Okay. So you have a drone, and that goes. That's not so more like navigation, but it's like a way of creating a map, right? Okay.
Oh, radar.
Radar. Okay. So like if you're on a, I guess. More like airports use this to see what other things are coming around, but they use this to make sure that air traffic control doesn't have any collisions, right? So radar, good. All right, so these are all, there's a lot of effort that's being put into like navigation and making sure which way we're going to. It's a huge industry. It's something that's particularly of interest to organizations like NASA or the military, but also we're seeing this now in like consumer products like cars and yachts, etc. Right? So there's like a big motivation to like make all these devices. Would you agree? Okay, so let's get a handle on like the required accuracy that some of these things need to have. All right. So would anybody be willing to venture to say that they come from or they live the farthest away from where we are right now? Who do you think lives the farthest in this room? Who lives or has or grew up the farthest away from this location? Okay, where'd you grow up?
San Ramon.
Where?
San Ramon.
San Ramon. Anybody farther than San Ramon?
Well, I grew up as well.
Oh.
In Pennsylvania, okay? Anybody farther than Pennsylvania?
My first 8 years in India.
India. Okay, can anybody beat India? Maybe? Okay, I think India is just about as far as you can get. All right, so how far is India from Palo Alto? 5,000? I think it's a little more.
I think it's like 5,000.
So let's use 10,000 as a nice round, easy number, all right? So we're gonna get an aircraft, and man, I don't even know how to draw this map. Let's say that we're gonna, okay, so California's here, right, Mexico, and then Palo Alto's here, and then you fly, and then here's like a really bad drawing of like Australia, New Zealand's out here somewhere. Asia's shaped like this, and then like over here you have India, right? And let's say that this is, yeah, Japan. Somebody said Japan. Okay. Somebody said that, okay, so if we're going to India, and just for sake of argument, this is 10,000 miles, right? How close do you think an aircraft has to get to see a runway? How many miles away can you be and still see the runway? Maybe 10 miles? Would that be with you? Okay, so you need to get within 10, after flying 10,000 miles, you have to get within 10 miles of the airport, all right? So this is the task, like the big boss, the CEO of the company comes to you as an engineer and says, I need you to create some device that we can put on an aircraft so that after we fly 10,000 miles around the world, we're only off by 10 miles, okay? Does that make sense? So do you think that you can get this with just a compass? Like we can run through the math, right? So like if we make this a triangle, and this is like the amount that you can be off by, and then like this is a really long triangle, there's a small little angle here. This angle, if we say like, okay, tangent of theta is approximately equal to theta, this is like a really cheap thing that people do a lot in graduate school. But this is equal to the error. We'll say that this is the opposite, and this is the hypotenuse. Okay, so this is 10 over 10,000. 10,000. So this is 0.001 radians. And how do we convert from radians to degrees? Does anybody remember?
Oh, 3 over 360.
So we have to take 0.001 times 180 and divide it by pi. Okay, and that's in degrees, right? Can anybody say? Does anybody have a calculator or a cell phone that can do this? Well, divided by pi.
Like 0.057.
0.057 degrees. Okay, can compasses do this? No, they can't. If you get into an aircraft in the cockpit and you have like any electronics that are on, the electronics themselves have magnetic fields. As you're flying your aircraft through the air, there's like charged particles that are hitting your giant like metal box, like that is an aircraft, and they're like causing like magnetic fields. So like magnetic techniques don't work to this accuracy. Okay? Now you can say that, okay, we can solve the problem with GPS, but I can give you at least 3 examples of other places where GPS might not work, right? Where you would need like a good system. So the first one, so GPS, for example, if we have our Earth right here, it's so nice, it's warm, it's hospitable, there's water, it's so nice. And there's satellites that are going around it, right? How can I make this not look like a TIE fighter? Here, that still looks like a TIE fighter. There, I think, okay, good. The satellite's going around here. The satellite is what tells you, you're right here because the satellite knows where it is, and then it tells you, I know where I am, this is where you are, right? But let's say that we send a Mars rover, and I have a really hard time drawing a Mars rover that doesn't look like Wall-E. But maybe, okay. And then we'll just give him arms. We'll just give up and make him Wall-E. Okay. All right. Does Wall-E have GPS? No, because there's no satellites there. So he needs something else, right? And we've already determined that like magnets and like compasses aren't going to do the trick either, right? This is one example where GPS doesn't work. Another example, let's say that, during this flight, let's say that something up here decided to launch a nuclear weapon and like destroy all the satellites. You'd be over this vast expanse of nothing but water and have like no clue like where you are. This could be like really bad. Like, oh, we're running out of like gasoline, mayday, mayday, mayday. And there's nobody that can hear you because like radio only goes somewhere. You can see how that's a problem, right? So, and another place where that might be a problem, let's say that you are in charge of like the USS Palo Alto. It's on water, and like you're over here, and like, but the problem is that while you're floating on the water, like some enemy decides that they're going to launch a missile at you. So here comes a missile, and like, what do you do if there's a missile coming at your boat? Like what would you do?
I mean, first you would construct a boat that, like, depending on your missile, if it determines the location by like reflecting light, then you might try to have like really sharp corners.
Mm-hmm.
So it could like.
Right, so stealth bombers do this, but sometimes like a boat is a really, really big target, and these things, can find it. So what a lot of people try to do is that they'll try to take another missile, a smaller missile, and then they'll like have it over here, and like it will You know, it will launch over here, and while this guy is flying, this guy will come out, it will loop around, and then come back and then destroy it here before this missile can hit the boat. It's kind of clever, but this is really hard to do. Why? Because if you're trying to steer this, like, have you guys ever been out with like remote-controlled aircraft? Has anybody ever done that before? A couple of you? When you go to the range, what are some problems that might come up with like your remote control aircraft when it comes to like radio signals, especially if there's lots of people?
It doesn't bind.
It doesn't bind? Why?
Because of all the signals disrupting it.
Right, so for example, there could be somebody over here with like, what's your name?
Dev.
Okay, so Dev is over here, and he's got like his little remote control, and he's like flying the rocket around, trying to like hit this one, right? But then this guy, he doesn't want to be hit, right? He wants to hit this. So this rocket is going to be engineered in such a way that it's just like screaming out like a whole bunch of like other like random like garbage signals, right? So that this little guy with his little, you know, signal is totally like drowned out by this. So you need to develop a system here that can't use GPS. It's not, you know, robust enough to use magnets, and you can't even rely on like radio technology. So what you need in, you know, this system, in this system, and maybe in a lot of other systems, is some device that you can put into a black box, and it doesn't need anything. It doesn't need radio. It doesn't need to see the sun. It doesn't need, you know, anything. But it by itself can keep track of which way it's pointed to better than this amount. That sounds like a challenge, right? Yes? No? Maybe some of you guys, this is easy? So this is the problem that I research at Stanford. Okay? There's a couple ways to do them, but most of the ways that people try to do this is by using some sort of fiber optics. Now, why would one person want to use like fiber optics for a situation like this? Does anybody have like maybe like a guess or a surmise or what about light or about photonics or, you know, like you know, shining a laser makes it so good for this type of application? It has something to do about the wavelength, right? Light reflects back, okay? This is a really small number, right? So if you want to measure something that's really, 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 really small, you need to use a really, 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 really small measuring stick, right? So the way that it works with a laser is that the laser, the measuring stick is about a wavelength. A wavelength, this is what we use to symbolize with, it's the Greek letter L lambda. What we use in our gyroscopes is only 1,550 nanometers long. For comparison, a human hair is about 50,000 nanometers long. Okay, so this is like a really, really small measuring stick. And so when you have a really, really small measuring stick, you can measure really, really, really small rotations, okay? So now that we have like a small measuring stick, we have to figure out a way to actually measure it, okay? So let's do like a little thought experiment right now, okay? So let's imagine that I never asked, how much time do I have? Am I like going way over?
No.
Got another 10 minutes.
Another 10 minutes? Perfect. Okay. So let's imagine that I was in this room right now, and I put a mirror in that corner, I put a mirror in that corner, I put a mirror in that corner, and a mirror in that corner. And I took a little laser pointer right now, okay? Is everybody's imagination working with me? Okay. So I take my laser pointer, and I shoot it into that corner. What's going to happen to that laser? It's going to bounce, and 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 it's going to come back to me, right? Now, if I shoot the laser this way, and I shoot it this way, are those two lengths the same or different? The same length, right? So this is a fancy, when you have a laser or a laser system, and you have two paths that are equal length, we call this reciprocity, or reciprocal. You know, like reciprocal means like this and that, right? Are the same. So now let's imagine that this whole scenario we just did, the room was not rotating. Now let's say that the room is like on the Earth, and the Earth is like rotating like this. Okay, your imagination's still working, right? The room is rotating, and I launch light both directions at the same time, right? So that you can imagine that there's two little photons, and they've got like the running shorts on, and they're like running as fast as they can, and they're having a race against each other as they jog around the room, right? Now, if the room is rotating and the mirrors are moving, are the two photons going to come back at the same time? This is kind of tricky, so don't feel bad if you get this backwards. No. One of them is going to go a little bit longer than the other one. I mean, you can almost think about this as like the room is rotating, so the finish line is moving, right? So like they launched from here, but while the room was rotating, I was like slowly drifting with the room, like as it was rotating around this way, right? So then they come back and they meet at the same time here, but this one passed me first, and this one still needs a little bit more time to get to me. Does that make sense? So what happens is that if we think about how light works, some of you may have taken like physics classes and you may have studied waves before. So if we have two waves, and the waves are like moving like this, right? And the waves are perfectly lined up. This is where it gets hard to draw. Low, and go high, and then low, and then high, and then low, right? All the high parts line up with all the high parts, right? And all the low parts line up with the low parts. And if I add these two waves together, what am I going to get? Yeah, it's going to be like really big, right? Okay? So if in the case where we took where the room wasn't moving, wasn't shining, and I shined the lasers around the mirrors, and they came back, what would I expect on the output? I would expect a lot of signal, right? Now let's imagine that the room is now moving, and then we shift this over. So now it's offset by, to make it simple, perfectly 180 degrees, alright? So now this signal is here, and then it's high, and it goes low, and it goes high, and then it goes low, and it comes back, right? What are we going to expect at the output now? It's going to be a different color, a different marker color. And it's going to be flat, right? So if the room is rotating, we would imagine, in this case, we would imagine no signal, right? So you're flying around the world, you've got a little box, and you're just looking into the output port of this laser, and like if there's a lot of flight, you know that you're not rotating, you're just traveling in a straight line. But now all of a sudden you're starting to veer to a side, right? And you see that amount of light that you see just fade away into a flat line. Does that make sense? Now you know that you're rotating. So the way that this works is that you take optical fiber, and optical fiber is like this wire that if you shine light into it, the light moves around the wire. And this is how, like, when you send an email, it launches light into a wire that says, "Hey buddy, how are you doing?" And it goes over to Japan, and your friend in Japan like mails you back, and it comes back, "I'm doing good, how are you?" Right? It's the same optical fiber that we use in telecom. We take a laser, and we shine it through optical fiber in a device that will pass it first to this port, and if light comes in here, it goes up to this port. We call this a circulator. This isn't important, but this is just how we... So the light comes in here, and then what happens is it gets split at a Y junction. Half of the light goes this way, half of the light goes this way, and then what do we have here? We have a big coil of fiber, right? Big loop. You can do it with one loop, but the more loops that you have, the more sensitive it is. It takes longer for the light to come around. Okay. So whenever you rotate this coil, you're changing the path length. You're sliding the second field right and left. And so if this isn't rotating at all, you put a power detector right here, and you get lots of light for no rotation. If it is rotating a little bit, then you have less light. The device that we're working on in our lab is sensitive to rotations as small as 0.0068 degrees per hour. So that's the sensitivity that we're able to achieve, which is better than this, right? So if we thought about, how long would it take, how many hours would you need to make this number as big as this, you could probably fly for like 9 hours and still stay more or less, pointed in the correct direction. So I think that this is all the concept that I can cover today. Like what I do is like all the fine little intricacies of like what happens here. There's some fancy electronics that we use to make this more sensitive here. Some small effects that happen here. But like my whole research probably, for the last 2 years and probably for the next 4 or 5 years is going to be focused on making this device better so that we can make this number smaller. So that's the bird's eye view of my navigation talk. If anybody has any questions, I can open up now for questions.
So when you put the laser to that, how do you make sure it splits into two?
Right, so the question is, how do we make sure that exactly 50% goes this way and 50% goes this way? There's 2 ways that people do this typically. One of them is called a directional coupler. And so what they do is they take 2 fibers. So this is a fiber that has light coming into it, and what they do is they shave off, let me just actually give this some help. So this is a fiber, right? I put some thickness in, but it's really, really, really small. And they take another fiber over here, and then when they connect them, they actually polish off some here, and polish off some here, so that when you put them together, some of the light leaks from one side into the other one, right? And then if they get the distance just right, they can say, okay, 49% is leaked, or like 51% is leaked, right? Over here, what they have is just like a fiber going through some material, and then it just splits in half, just like you would like a faucet, and you would hope like 50, yeah. You want it to be as close to 50% as possible. It's not always like achievable. Sometimes you have 40 or 60, but it actually doesn't matter that much, because if you do the math and like 40% goes around this way and comes back here, that means that 60% of this light is going to make it back in here. So that's 40% times 60%. Now the other way, 60% came around here, which means 40% is going to come back. So it's the same number when you multiply it both ways. So it doesn't have to be 50, but you get the most power and the fewest bad side effects when you get close to 50.
Great question, Serena.
Can you re-explain how the fibers rotate and what do they mimic?
Well, let's say that this is my like gyroscope right here. Inside of this gyroscope, it's usually bigger, but there's a laser here, and there's a circulator here, and then there's like a coil of like 100 meters of fiber wrapped around here. And I put this laser in like an aircraft. So let's say that Jonathan now has become an aircraft. He's flying. Oh, it rotated. Oh, it rotated. So I carry this eraser around with me wherever I go, and that's where it. And so the rotation happens whenever this eraser moves like this. Does that answer your question?
Mm-hmm.
Okay. Other questions? Yeah.
Was there a previous method before like this technology?
Yeah. How many of you guys ever played with like those like, man, they're like witch magic, like gyroscopes? Like you like put a string around them and you like wind them up and you like pull it and you like can like hang in it, like defies gravity, and yeah, that's what they used for a while. But the problem with those is that there's this thing called precession. So you've probably noticed that when you like take one of those gyroscopes, or even like a top, and you put it on the table, it like it wobbles around like this, right? So that was a problem that they would have to like always compensate for. And they compensate for it some, but that rate of precession really depended on how quickly it was spinning. So they had to make sure they were controlling how fast it was spinning. It got more accurate if they made it faster or if they made it heavier. But if you think about an aircraft where power and weight cost money, a lot of money, you don't want to have something that's big and requires a lot of power to make it spin faster. So up until like maybe about the 70s, people were using mechanical gyroscopes. And then around the 1970s, when they started coming up with this technique and another device that works similarly to this, but fundamentally different.
Great question.
Time enough for one more.
Okay.
Can the coil tell what point it's rotating around?
Can it tell like what position it's rotating
Yeah,
about?
like if it's rotating around the point, if it's going around the point out here, can it tell?
Oh, so you're saying like if so does this know whether or not it's doing this or whether it's doing this?
Yeah.
One coil by itself can only detect like both of those things look the same to it, right? Because it doesn't have any knowledge about where it's moving. It just has knowledge about where it's pointed. So this thing has to team up with something called an accelerometer, which does the same thing. Instead of rotation, it does it with actually like jostling back and forth. And then together those two are able to put together the big picture of where the universe is. Yeah.
Great question.
Great question.